Okay, let's start with the module video and some of the fractals that were named in the module video. Can you guys tell me? There were three main ones that I kind of want to talk about. Can you explain, or can you give me names of those three fractals that were mentioned in the video or shown in the video? Okay, cool. I'm seeing Sierpinski gasket, which was one of them. Yes. So this Sierpinski gasket, which we'll draw, and then there was the Sierpinski carpet, and the Menger sponge. Okay, I'll kind of talk about how these are oriented. The Sierpinski gasket is essentially formulated by starting with an equilateral triangle, and then removing equilateral triangles from this triangle. So we start with a triangle that has all of it's a filled-in triangle essentially, and then remove we connect the midpoints of the three sides. So we connect those, and we remove this central triangle from the figure. And now we have essentially three copies of the original triangle, just smaller, right? And then we continue this process again. So we have three copies of the original triangle, but smaller. So then we do the same thing. We connect their midpoints. We connect the midpoints of the sides, and then we remove that central triangle. We do the same thing with this bottom left-hand triangle. Right, so the fractals are formed by repetitive processes like this, where we do the same thing over and over again. And then if we ever zoomed into a picture of a fractal, so for example, if I zoomed into here, we would see exactly the same thing as if I were looking at the whole picture. So we continue this. Now, after doing it a second step, so that the first step was removing this central triangle. The second step is removing these three triangles from the original. And so we've now formed 1, 2, 3, 4, 5, 6, 7, 8, 9 triangles that are identical but smaller to the original big triangle. Those are equilateral triangles. And then we repeat the process. We connect the midpoints of each of those, and we remove. Right? So it's a very repetitive process, but every step of the repetitive process is defined the same way. And so after each step, we can analyze the figure in terms of finding its area or its perimeter, or in the case of the Menger sponge, we can talk about its volume after each step of the process. So now I've done three steps, and I have probably 27 copies of the original triangle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. I have 27 copies of the original triangle, but smaller. And if I were to zoom into any part of this, for example, if I zoomed in here, we see an exact copy of the original triangle. Now, it doesn't look like the exact same copy because I've done more steps on the original triangle than this picture here, if I were to look into the top triangle here, I've done less steps of the process on that one. The idea of a fractal is that the process, the steps, is done infinitely many times. So no matter how far you zoom in, you always see the same picture. So that's the Sierpinski gasket is with triangles. We essentially do something very similar with the formulation of the carpet. So the carpet is kind of a square version of the gasket. So we start with a square, and we imagine that it is split into kind of like a tic-tac-toe board where you have equal squares, 9 equal squares in here. And then we take that center square and we remove it. Right, removing that center square essentially creates, leaves 8 of those identical squares from the beginning, right? So there's 1, 2, 3, 4, 5, 6, 7, 8 squares remaining in our carpet. And now for each of those squares, so for example, this top left corner square, we're going to cut that into a kind of a tic-tac-toe board and remove the center square. So we'll have this center square here removed. Same thing with this top square. We'll have the middle square removed, and so on. So we'll have this middle square removed out of that one. We'll have this middle square removed. I guess we can leave like the guidelines for the original segmentation, just so we know what we were dealing with. So that was the original cutting where we removed the center square, and then for each one of these, we cut each of those squares into 9 little squares. And we remove the middles. I'm only going to do 2 steps of this because cutting those into smaller squares would take years off my life. So we're just going to do, we're going to complete this step and then we'll be done. So removing those middle squares, the ones we're removing are this one, this one, this one. And so those middle squares are removed. And then we have so many little squares to deal with. There's, what is it, 1, 2, 3, 4, 5, 6, 7, 8, 9 by 9, which means there are 81 minus these 8 removed. So there's a bunch of little squares. And each one of those little squares, like this, for example, this top left corner square, we would be removing the center of that square. Right? So you can infinitely continue this process to generate the Sierpinski gasket. And then the Menger sponge is a 3-dimensional version of the Sierpinski gasket, which means I'm going to draw a cube here. Right, and then I'm going to cut the cube into, or each, yeah, I guess we're essentially forming kind of like a Rubik's Cube situation here. We form a Rubik's Cube. And removing the center square or the center cube from each of the sides, and then also the very middle cube as well. And then each of these little cubes, like this cube up here in this corner, is a copy of the original cube that we started with. So then we'll do the same thing on that face and remove the center squares on all of these cubes on all of the sides. Right, so all of these little cubes would be removed from those cubes, and we get a two-step iteration of the Menger sponge as a picture. Now, very interesting things about these fractals are kind of the surface area versus volume conversation. For example, the removal of area or the removal of volume when done infinitely means that as we continue this process for the Menger sponge, the volume of the cube that we started with, as we remove more and more pieces, approaches zero. So if you were to do this infinitely many times, there is no volume left in this cube. So it's just like it becomes all surface area when done infinitely, because as you remove cubes from this cube, the surface area increases because you're creating new surfaces. When you remove a cube from in here, that just creates more faces inside of the original cube. And so while the surface area increases, the volume decreases down to zero. For the two-dimensional alternative of that, as I start cutting these triangles out of the, let's say, the gasket we're looking at, as I cut this out, my area obviously decreases, right? We started with an area that was this big triangle, the whole area of the triangle we had, and then we cut out this middle triangle, which means we cut our area into like 3/4 of the original area. And then the more and more we do this process, the area gets smaller and smaller, essentially approaching zero, the more triangles we take out. But if we talk about adding the edges of all of the sides of the triangles that we have, all of these side lengths added together keeps growing. Every time we do a step, all of these side lengths, there are more side lengths. Granted, they are shorter, but there are many more side lengths than we began with. So the perimeter actually, does the perimeter increase? I think it does, yes, because we still have the original perimeter here. All three sides of the original triangle are there, but we've now added a bunch of new sides to add to the kind of a total perimeter for the figure. So we're going to, in class, do an example of the Koch snowflake, which is going to be, the process is going to be explained here, and I'll kind of briefly go over what the process is, and then we'll talk about, on the second and third page, we'll evaluate the perimeter of the first couple of steps, the first few steps, and then we'll come up with a perimeter for if we were to continue this infinitely many times. And then we'll also look at the area of the first three iterations, and then I guess we're not talking about the area of the final figure. But let's talk about the process. The process says we start with an equilateral triangle, so kind of like the Sierpinski gasket where we started with a triangle, we're also starting with a triangle in this one. Now it's oriented a little bit differently. It's not standing flat on one of the edges. It's more like a play button than a vertical up arrow. So we're starting with a play button triangle, equilateral. Step 2 says in the middle of each side of the triangle, attach a smaller equilateral triangle pointing outwards. So that means that we are taking a side, so this side here. We're going to do it for each side, but I'll show you how it's done for this side. So we take this side and we say in the middle of this triangle, we're going to cut it into 3 equal segments. So that's about 1/3. I'm going to put a point at 1/3 and a point at 2/3 of the way across that side. And I'm going to build a equilateral triangle on that segment. So in this center segment, I'm going to build an equilateral triangle. All right, we're going to do that for all 3 of the sides. I'm going to take this one as well. I'm going to build an equilateral triangle on that side. That one's kind of small. And then we're going to do it on the 3rd side as well. So we're going to cut it into thirds, and we're going to build an outwards facing equilateral triangle on all 3 sides. And then step 2 is actually missing a vital piece of information. This is supposed to turn into this as the 2nd step. So it's supposed to go from this to this, which means we have to kind of get rid of these attaching pieces, right? So when I build this triangles on the 3 sides, I actually need to delete these bases in order to get this 2nd piece of the snowflake, right? So we're going to add a little instruction here. Oops. We're going to add a little step here that says remove the side of the smaller triangle attached to the previous side. Meaning these 3 little sides of the little triangles are going to get deleted. Right, so if you want to put a little X mark on those, we're going to delete those 3, and that's it. That's the whole process. So that gets us from the first original triangle to the second, 6-pointed triangle. Right, there's 1, 2, 3, 4, 5, 6 points now. And then we repeat the process. So to go from here to here, we're going to take each straight side length, so like this one, for example, and we're going to do the same process. We're going to build a smaller 1/3 sized triangle on that side, and then delete the side that's touching the original triangle. So I'm going to cut this side into 1/3, and I'm going to build a triangle on this. And then I'm going to delete that side that's touching the previous figure. Right, and we're going to do that for every single, we're not going to do it, but this is how we get to the next step, is we do this process for each of these sides, right? You do it for that one, we do it for this one, we do it for this one, we do it for this one, and so on. So every single original side that's in this 6-pointed snowflake, we add a new triangle onto their sides, and then we end up with this picture once we've deleted all of the sides that are, all of the bases of those triangles. So we see figure 1, figure 2, figure 3, without all of my additions, obviously. So I was just showing you how we get from here to here, from figure 1 to figure 2. These are not part of the first figure. The first figure is just this triangle. Right, and figure 2 is just the 6-pointed snowflake. Figure 3 has, how many points would it have? 2 became 3, 2 becomes 3, 3 becomes 6. I actually don't know how many points this has. 1, 2, 3, 4, 6, 6 times 3 is 18. I think this has 18 outward facing points. Anyway, what we're going to do is, so then the snowflake, we do the same process again. It goes to figure 4, which would be this one. figure 5, and figure 6, where you can't even tell what the sides even look like anymore because it's so fuzzy and there's not enough pixels on the paper to kind of show what the triangles or what the points look like on this snowflake, right? But if we were to zoom into like this part of the snowflake, it would look exactly the same as this part of the snowflake does now, right? So if we zoom in to any part of the figure, it looks similar to what we see in itself. So what we're going to do is we are going to, or you are going to, find the perimeter of the first 3 figures, which shouldn't be that bad because remember for perimeter, so if we were to start this example in perimeter 1, we have this equilateral triangle. P1, it tells us that each side is of length 1 foot, which means I have a triangle that's 1 by 1 by 1. So if I do, as far as perimeter is concerned, I would do number of sides, because all of the sides are the same length in each step of the way. You can do number of sides times the length of a side to kind of shortcut the process. I know this one is easy enough to just say 1 plus 1 plus 1 is 3, but when it comes to like this third picture, you really don't want to say like this plus this plus this plus this plus this plus this. You don't want to add all of those sides together, right? You kind of want to have an idea of how long each side is, and then how many sides there are, and just multiply those two values, right? In this case here, in the first picture, we have 3 sides, and the length of each side is 1, so we get 3 feet as our perimeter. Right, so you kind of want to do that for P2 and P3. You don't necessarily have to draw the whole snowflake for P3 because it is pretty hard to. It's a lot of drawing to do, but you might want to draw it for P2 just so you can count the sides, and then do this perimeter calculation where you multiply number of sides times the length of a side. Any questions so far on how we're going to do perimeter for each of these figures? Okay, let's talk about area. Area is a little bit more interesting because we're essentially finding the area of a triangle, which I'll draw the first one here, where each side is length 1, but we want to find the area. And if we think about the pictures here, we have the original triangle. So let's say that has some area, right? It's just however much stuff fills in this space. But we see that in the second picture, we still have all of that space, right? Because of the way the process works, we still have all of that space. We're just adding more triangles onto the original area. Right, so the area is just going to strictly increase from the first step to the second step. And then in the third figure, we still have that original triangle area. All of that area is still there. In fact, we still have the area from the second step as well. Right, if I outline this correctly, we see that in here we have all of figure 2, we're just adding a bunch of little triangles onto it, right? So the key idea here is going to be figure out the area for the original triangle. And then when you want to do the area for figure 2, figure out the area for one of these little triangles and add 3 of those onto the area of the original triangle. And then going from figure 2 to figure 3, once you have your area of figure 2, once you have that area, you figure out how many of these little triangles we're adding and find the area of one of these guys, and then multiply by how many we're adding around the figure, and then add those to the area of figure 2. So let's talk about the area of one of the first figure, because area is not, for area of a triangle, how do we do area of a triangle? Yeah, 1/2 base times height is our area formula. So area of a triangle is 1/2 base times height. Now, we don't have the height of this triangle. The height would be the distance from one of the sides to the peak on the other side. So it would be something like this would be h if I call this side the base. The height would be that the length of that dashed line from one side perpendicularly up to the peak on the other side. So we actually need to find that height if we want to find the area. We could also use the other equation, which might actually be more useful. Let's not do this. I think I want you to do it the other way, because it's going to be more useful in this situation. It'll be good practice for using the other formula. What's the other formula for area of a triangle? The one with the S. Remember, we had a different formula if we had all 3 sides given and we didn't have the height given to us. We had a formula that was like a square root. Anyone remember? I know there was an S in there somewhere.
Wasn't it like the perimeter multiplied by the each of the side lengths, something like that?
Kind of.
And then it was square rooted at the end.
S was S had to do with the perimeter. S was 1/2 of A plus B plus C. So S was half of the perimeter. So that part, yes, it had to do with the perimeter in that case. But the square root one, this is 1/2 the perimeter, which we have from the first 1/2 the perimeter we have from the first page. But inside the square root, we had Michael has it correct. We have S times S minus A times S minus B times S minus C. Let's try to do it using this formula. I think it's going to be useful. So S in this case will be 1/2 of 1 plus 1 plus 1, which is 1/2 times 3, which is 3 over 2. And then the area of this is going to be the square root of 3 over 2, parentheses, 3 over 2 minus 1, 3 over 2 minus 1, and 3 over 2 minus 1 again, because all 3 sides are just 1. Right, so the formula is not that bad here. We have a square root of 3 over 2 times 1/2 times 1/2 times 1/2, which is a square root of 3, whoops, I don't need it that big, 3 over 16, which we can square root the 16 on the bottom, which gives us square root of 3 divided by 4. So that's our area for the first triangle, the beginning triangle of the snowflake. Any questions on the first example with the area? I'm going to give you an idea of how to do the second one, but I'm not going to do it. So for the second one, I would recommend drawing the first triangle. Right, we have the first triangle that are side lengths 1, 1, 1. But then what I'm interested in is I still have all of this area. So I still have the square root of 3 over 4 in my second piece of the snowflake. Instead, what I want you to focus on is I want you to draw, cut this into thirds, draw a triangle on top of that, and find the area of this triangle. Because if you find the area of that triangle, you can just add 3 of those. You can add 3 of those to get the total area for the second step of the figure, right? If you find the area of this little triangle, you can add 1, 2, 3 of those to this square root of 3 over 4, and then you'll have your area of the second figure. Okay, and then you'll do that again for the next one. You'll find the area of one of these triangles and add however many of those there are going around the picture to the area of figure 2. So you kind of build up the areas as you go. You'll start with the square root of 3 over 4 for the first one, and then this answer will be square root of 3 over 4 plus something, and then this will be A2, which we find in this step, plus some more triangles added to that second answer, right? So those are going to build on top of each other, whereas these ones I would do individually using this, this idea of the number of sides and the length of a side for each step of the snowflake.